have the great privilege of introducing now our next speaker, which is Tom Pilette. So Tom Pilette has over 30 years of experience in automotive manufacturing and batteries, and was former business development head of Magna International, which is a major automotive supplier, and now is chief operating officer at a startup called Zeta Energy that is producing a revolutionary new battery technology. And I'm so excited to hear your presentation, Tom, so I'm handing it over to you.
Well, thank you, Melissa. Thank you for that nice introduction. Appreciate it very much. As Melissa said, I spent a tremendous amount of my career in the automotive industry, more than 30 years, focused on delivering innovative products into the global automotive market. And namely, a lot of those that you may be aware of most recently are really evolving around the major trend towards either electrification or autonomy functionality. And we're going to talk a little bit today about an innovative or breakthrough, a bunch of different innovative or breakthrough battery technologies. And I thought I might share a little ice-breaking video with you here today. And we'll start with that, and then I'll talk about why it's relevant to some of the technologies as we talk about what is truly disruptive and what is truly game-changing as we look at the landscape of really creating a real opportunity for sustainable energy across multiple industries, but today's presentation is going to focus more around the automotive space. Well, thank you. I hope you found that a little entertaining, and it's going to be relevant as we go through the presentation and we talk about some iterative improvements in battery technology at the cell level, and we start to then move into what we think could be some true game-changing technologies as we get further into this presentation. So with that, I'll share my screen. And so, you know, we look at that little, I call it a tongue-in-cheek little spoof on that video as we played it here today, and we talk about 10,000 cells in an automobile EV battery. But that's really not unlike what you saw in the first generation of Tesla vehicles in the Model S. And we're going to get into a little bit more of a comparative about existing or current technology versus the idea of transformational or disruptive technology as a future play, creating a super growth market in an area like automotive electrification. And really, I thought Melissa did a wonderful job talking about the definition of innovation or transformational or breakthrough innovation. And I won't spend a lot of time on it, but they are very rare. And it's very important to really separate the difference between something like continuous improvement and a technology that really could be game-changing or breakthrough. And so the real difference is that the idea starts somewhere, usually generated by a need, in this case, an opportunity of sustainable energy or a growth market like EV automotive, and then a lot of real hard work goes into addressing some of the transformation. And we're going to talk a lot about that today. I liked how Melissa also captured Thomas Edison. I believe he was an icon in innovation, and we're going to talk a little bit more about him as well. And so we always have to look back at innovation as we start to really envision where we think the roadmap can take us. And so the battery is nothing new. And in fact, the Baghdad battery was thousands of years ago, a simple form in a clay pot that was theorized it was used to do gold plating on different metals early in its time. And then fast forward into more recent history, and we talk about the name battery. And Ben Franklin coined that name back in the 1700s, mid-1700s time frame. And then we continue to fast forward on the continuum, and I love this little graphic across the bottom. Again, it's this continuing play on the AA battery that we have in this presentation. As we look forward, we start to look at rechargeability, and we start to look at the introduction of a simple technology or a newer technology in the 1800s, like lead acid and the rechargeable lead acid battery. That's going to be sunset claused here in the very near future, and we're going to need to look for different and safer chemistries that will replace not only high power, high dense technologies that we're going to need not only in automotive applications, but just about every free power application that's out there, including support for the grid and local energy independence. And so we fast forward into really motivating driving factors in the growth of certain product areas like the laptop computer, and we look at batteries like nickel metal hydride, and then the progression into the first introduction of lithium ion. And lithium ion is not a new technology. Lithium ion's been around since the late 80s, early 90s, and it's been commercialized in very high volume since the early 90s timeframe. And it's gone through a significant amount of iterative development. And so now we look at the technologies that are really going to transition us and take us into the next generation of electrification of both products, technologies, and industries. And so, as I said early on, because my background is primarily coming from the automotive industry, I really wanted to highlight this new emergence transformation into the electrification space that's really been spurred by companies like Tesla. And we're going to talk a lot about how that motivation really captured the imagination, not only of the public, the buying public, for an energy independent or sustainable energy type vehicle, an alternative from fossil fuels, but also how that really kickstarted the rest of the global automotive market. And so we don't really have to question whether we're going to see a transformation into electrification. We know it's happening. We know that it started very early on in the 1990s with really small demonstrations of technology, and then accelerated into the early 2000s with the onset of companies like Tesla, who really sparked the imagination of existing and very powerful global OEMs that we're all very well aware of, household names, and really kickstarted them to start to envision a roadmap where they would have to introduce a transformation from ICE engine to electrification. And it wasn't a question now, as we look forward in 2020 timeframe, it's not a question of if or even when. That's been answered for us. It's clear the timing is today, and we are really starting to see a catalyzation out of companies like Tesla. And so I wanted to share a little bit about the timeline and the transition into electrification, and utilizing Tesla is what I believe to be that catalyst. And so you start to look at how early, we're talking about Ford Motor Company, a company that's been around for 100 years, and General Motors and Daimler, the companies that invented the premise of the petrol gas engine automobile. And so we have this company that's founded in 2003 and brute forced a technology, an existing technology, into an envisioned electric vehicle platform. And they did it in a very unique way. They utilized existing technology. They envisioned a roadmap where they could improve that technology, and brought forward utilizing a brand new approach to automotive ingenuity, to electrification. Many models since then, and in just the last 10 years, have expanded those models fourfold, and have now gone from what was the first demonstration of a gigafactory in Nevada to what will be their next several investments in battery manufacturing, most of that in-house. And that's going to be at the Tera level, a Tera factory, 20 times the capacity of what is existing in the Nevada Gigafactory today. So I'm not going to talk a lot about the data that's on this chart today, but I really want to reference and highlight the fact that you see every one of these hockey sticks, whether it's in energy demand or the increase in gigawatt output that meets the need of electrification needs in the very near future, now and before 2030 timeframe, but also the substantial revenue market that it creates. What we're showing here at $170 billion is a pretty conservative estimate, and it's only addressing the pack level, the cell and pack level value of the electric vehicle. If you include the entire transformation up through and including 2030, you're talking about $1 trillion industry. And you couple that with the impacts that are created with electrification, and then the adaptation of autonomous functionality, you can quickly start to envision multiple service-related industries that are built around those two transformational technologies in a very exciting market like electrification and automotive space. How do we get there? And that's always a challenge. And so, there's a lot of thought process around existing technology, displacement of existing technology, and the time frame to do so. In my experience and in the history that I've been involved in automotive, it really comes and it meets a nice pinnacle. And that pinnacle is when you have a crossover point, when you have a cost parity, or you have a performance improvement, or you have a dependency reduction on something that really transforms the industry. And so as we start to look at cost parity between an internal combustion engine and an electric vehicle, or in this case, a battery electric vehicle, we really start to see, as the cost of the cell pack level come down over time, which have really accelerated since the 2015 timeframe, we can really imagine that there's cost parity between an ICE engine and an electric vehicle well before the 2030 time frame, which is suggested in the chart on the left. And so by all accounts, as we start to see the rapid improvement of technology at the cell level, we expect cost parity to really come to play in and around the 2025 timeframe. That really drives the innovation and growth that we saw on the previous slide. And you start to look at existing capacity that's installed, a number of gigawatt facilities that are up and running, and more being announced daily to meet this demand. You got to ask yourself, is it real? Do we see this growth? Do we see this realization in this time frame? Well, let's take a quick look back, and I can assure you that it is. And I can almost guarantee that some of the predictions that even Elon made, this week was an exciting week for us in the battery space. Tesla had their board of their shareholders meeting, and they also had their battery day. And I'm going to share a little bit about that with you here in a few more slides. So battery prices, and this is important to see, are really measured not only at the cell level, but at the integration level within the electric vehicle. We call that a module in a pack. And so as you look at the transition of costs over time, and we're going to break that down in a couple of successive slides here in a moment, you'll start to see why we think that there's real opportunity to meet that cost parity crossover point in an extremely short amount of time. Look at the reduction in costs, say, since 2013 at the cell level. We've halved it. And we expect that we're going to have that cost again within the next 2 to 3 years. And so as you start to look at these are all different data points that I compiled together in this presentation, and they all agree. And that's a good thing when different data points start to agree and they converge and they speak the same language. An incredible market opportunity if we have the right battery technology. And so let's take a look at that for a minute. And so the previous slide talked about the cost at the cell level. Here's a bit more breakdown of what that cost really looks like. And you can see that staggering reduction in overall cost. I want to focus on the chart on the left, and I want you to focus on the olive green cathode cost. And you'll see that over time, as we start to improve not only the material cost of the cell, but we've also taken dramatic steps to improve the manufacturing throughput of the cell itself, whether that's at the pack module, but for sure, those cost improvements are represented in output, throughput, process improvement, process speed at the cell level. We can't lose sight that at some point, and we're starting to see that, the iterative improvements that are being made, and they're rapidly being made across the entire globe, you really have to focus on raw material costs. And that's why I wanted to highlight the cathode in this slide. And we'll quickly look over to the right, and you look at the expectations of cost, and you see 68% the cost of a cell is in the raw material. And we're going to get into that in a little bit, next couple of slides. But think about 68%, and then the chart on the left shows the cathode being a majority of those costs. And this is where this presentation is going to focus on where I think we can generate true breakthrough or disruptive technology. So I thought it might be interesting, if you're not really into battery chemistry or you understand the cell itself, to talk about the different formats of cells. And then we can get into a little bit more around something that's really relevant to everybody. And it's the battery that everybody's talking about, the battery that's in a Tesla, and the next generation of technologies that will drive not only Tesla, but a whole industry in electrification. And so a cell can be made up of many different form factors. A cylindrical cell, like Tesla uses, and what was the first generation Panasonic joint venture, an 18650 lithium-ion cell. It could be a very small form factor like a button or coin cell, and that could be something that's that's utilized in a hearing aid or a microphone or a small medical device. And then you start looking at more personal products or products that you may be utilizing today, power tools and others. Those are prismatic cells. And then finally, we're looking at large pouch cell formats. Pouch cells really drive the ability to increase the amount of material, the amount of active material, the amount of safe performance between the anode and the cathode. And I'm going to talk about that here in just a moment. So as we look at the number of cells, and you'll reference the humorous video we had in the beginnings of Tesla also used thousands of small cells. And they did that for a very specific reason. They did that because that was a known entity at the time. It was well understood. It was in high volume. It could be manufactured at a very high rate of speed. And so what Tesla did is found a way to very elegantly bring that into a pack module solution in the first Model S. It wasn't the most cost-effective solution. It wasn't by far. However, it was a solution that brought that vehicle to market very quickly and with a relative amount of safety. And so you've heard about things that Tesla has gone through over time with battery fires, thermal runaway, increased innovation in battery management systems to protect individual cells and modules within both I'll call it the beginnings of their battery electric vehicles, and how they've then managed to iterate additional safety and transform their current cell technology, which is a large cylindrical cell, into a larger format, and really optimize and reduce the number of cells, thus innovating and reducing cost at the same time over about an 8-year period. And so I'll share a little bit about that in the battery day. And so this is a very busy slide. I had an opportunity with some very interesting folks who wanted to challenge this slide yesterday. This is a slide that was put together out of all the innovations that were presented on Battery Day this week. Elon and the top executives within Tesla promoted multiple technologies that together, whether it's in the battery itself, whether it's in the battery chemistry, whether it's in the battery manufacturing, the size of the battery, or the integration of that battery into the vehicle, would reduce the overall cost at the cell level of the battery, of what they are manufacturing, what they're paying for, by 56%. And so it's really important to really not just look at each one of these technologies as an individual innovation, but as a whole, you really start to see the value of the cost reductions that were promoted in the first several slides. So this really highlights the growth of the opportunity just in this slide alone. When you start to look at energy demand or battery demand of Tesla and Tesla products alone over the next 10 to 15 years, they start with about 1/10 of a terawatt. And that's where they're at today. And that's what they have forecasted for all the models, including Cybertruck, some of the heavy truck developments that Tesla's engaged in today. But fast forward 10 years and you see 100-time capacity increase. And that's astonishing when you think about the level of investment and you think about the rapid growth rate that we see in this industry. And this is just the point of view of Tesla. And so if you break down the battery and you start thinking about the anatomy, this is where we really get into the value. So we think about active material and we think about a safe performance of the battery. So a battery is made up of two current collectors. These current collectors are electrodes, the anode, a negative current collector, and a cathode, a positive current collector. They're separated so that we can both discharge and recharge efficiently without running to ground. And so we do that by using either a liquid electrolyte, or in some cases, and we're going to talk about this here on the next slides, a solid state electrolyte. You can also envision a solid state electrode. We do this by moving ions across the media, thus discharging and recharging energy as we see fit. The chart on the right really highlights the previous slide of cathode cost importance in battery innovation. And it's not just the cost, it's also the safety. And so when we look at trying to drive true innovation, whether it's increasing energy density, significantly improving power, or we think about providing a safer environment for the cell itself, reducing thermal runaway, we have to look at the chemistry inside that battery. And we're going to break that down over time. So the real game-changing technologies are coming from companies that are currently developing next-generation chemistry. And so those next-generation chemistries are really driving innovation into both sides of the battery. They're reimagining both the anode and the cathode and how they will safely exist together in a cell that will provide not only higher power, higher density, longer cyclability, which means longer duration of use. It also means they have to do this in a very safe way. And I chose the picture of the Oxys pouch cell up in the right-hand corner, and they drove a nail through it to prove that they couldn't short that real early prototype in their particular chemistry. And so I'm going to talk a little bit about the uniqueness of the two sides of this slide next. And so if you start thinking about everything on the left-hand side, these are the guys that are introducing technologies that really are formulated around solid state technology. And solid state can mean a couple of different things, as I mentioned earlier. Solid state might be a solid state electrolyte, which provides the barrier between the two electrodes, or solid state could mean that you have solid electrodes with a solid state separator as well. And so each and every one of the companies, Solid Energy, Solid Power, QuantumScape, all address that solution differently and with different chemistry. And each and every one of them, early in their development, have claimed that they have breakthrough, that they have transformational technologies, and as such, as startup companies, garnered a tremendous amount of attention. And they garnered that attention not only from the automakers that need this technology, they garnered it from the current battery producers. The largest battery producers in the world were also very interested on whether these startup companies could progress this technology across the finish line. The technology companies on the right have addressed the solution a little differently. They looked at the value of the battery. They reimagined the value of the battery by using very low-cost input elements, components, and chemistries. And I have the pleasure of working for and with one of those companies, Zeta Energy, and I'm going to spend a little bit of time in talking about why we believe we have that next generation breakthrough technology. And so each company on the right addressed a critical aspect of the cell's performance and the cell's cost, really highlighting two key factors. So really removing themselves from the known technologies of lithium ion and looking at how they could take the technology and expand the performance of the cell, all while providing a safe environment for the cell to operate for a very long time. And so when you start thinking about materials like cobalt and nickel, which are very expensive, $30,000 a metric ton, $15,000 a metric ton, and you replace them with a material that's $100 a metric ton or $40 a metric ton, you're starting to see a transformational change at the cost side of raw material input. So I'll transition here to the next slide. And so I don't have a tremendous amount of what I'll call data and charting, but I do want to share something with you that we're doing at Zeta Energy. And so really this is a section of a spider chart where we really highlighted cost, energy density, and power density, and we compared that to a current state lithium battery. And as I mentioned, what we've done at Zeta Energy is reimagine both sides of the battery. So we created on the anode side a carbon nanostructure that we grow directly onto the current collector. So we use a copper current collector, and in situ, we developed the growth of a 3D nanostructure carbon element using carbon nanotubes, and then we pair that with a very efficient and very robust and safe sulfur cathode. And so we've taken what was a problem area, which was sulfur cyclability, and using advanced chemistry and breakthrough developments, we were able to stabilize the sulfur so that it would perform for a very long time. Using a very low-cost cathode, using a very efficient anode, putting those two together in an ultra-low-cost cell, we were able to come up with an innovation that functions very, very efficiently at temperature, at cyclability, at very high charge rate, and at very demanding discharge rate. And we did that addressing each individual element of the battery and breaking it down, taking a look at post problems, taking a look at future opportunity, and developing a cell structure that really addressed all the current issues that were available or that were happening with current state lithium ion technology. And so one of the things that we have to always remind ourselves is that even when we have breakthroughs, whether it's in chemistry or whether it's in physics, whether it's in processing, just having a good idea at an electrode level or a cell level isn't enough to say that you can transform or game change an industry. Once you have that idea, You really have to take that idea and you have to really work very hard with a very seasoned team of individuals who can take and rapidly industrialize that technology. And we were very fortunate at Zeta to really bring on very, very high level, high talent, very long tenured individuals in their fields for one very important reason. And that's because they saw the value in what was invented and knew what was invented was going to take a team of well-established, well-represented, well-connected individuals to get it across the finish line. And when you can get it across the finish line, then you can really state that you've changed the game. You've got a game-changing, transformational technology. Melissa had Thomas Edison in there, and she talked about his tenacity. I agree. Extremely tenacious, brilliant, driven, so very focused. But even after he had an invention, Thomas Edison went to work for very long hours in his laboratory. I love this picture. You see all the fruits of his labor behind him. This is his environment. This is his workshop. It's his toolbox. Vision without execution. So great idea, but a roadmap to get that idea to a commercial success is what it takes. And so it's a lot around hard work after you have an innovative idea. And with that, with the implementation of that idea, you can transform not only an industry, you can transform the need of energy independence, and you can really develop, rapidly deploy sustainable energy solutions. And we all know today we need rapid deployment of sustainable energy. You don't have to look any further than what's happening with global warming, the fires in California, to know that with the right battery technology, not only can we drive an automotive EV rapid transformation, but we can drive sustainable energy solutions.
Okay, if I caught you right at the end there, Tom, is that the last slide? Excellent.
It is.
Thank you. Nice. All right, so we only have a little bit of time for a couple of questions, and we have one question right now from the Q&A board that asks, what about the recyclability of batteries? Like what about the pollution that's endemic to just manufacturing all of these batteries and disposing of them?
Yeah, and so that's a great question. And so the industry's been looking at the responsibility of end of life, especially the electric vehicle industry, for quite some time now. And so Elon made a statement in his battery day, and I'll use his statement, and I'll talk a little bit more about it. Tesla expects that they will be recycling 100% the raw material out of end-of-life vehicles at a sustainable rate within the next 3 to 5 years. And so they're going to consume all of the valuable minerals, the materials, the chemicals that are inside those batteries and start a sustainable recyclability process. They're not alone. There's many other global companies that are doing that as well. Most of them are focused on certain elements of a cathode or certain elements of an anode, and they're turning those around into brand new anode and cathode businesses.
Okay, so you see them as being largely recyclable.
Oh, absolutely, largely recyclable. There are other uses. We can actually use them for a different purpose if they have valuable life left at the end of we'll call it the drive cycle. They could be used as a power wall. They could be repurposed to support grid support, things of that nature. But moreover, I think the biggest opportunity is going to be the responsibility to reconsume those minerals and those materials.
Gotcha. Now, you had a slide that showed a bunch of different startups, and you mentioned that they were all pursuing different methods of developing a better battery, including different chemistries and focusing on different parts of the battery. And I know your answer is going to be kind of biased here, but trying to not be biased, how do investors navigate that? Like, that would seem to be a very uncertain environment. How do they decide which of these technologies to back, and are there even metrics to look at to know who to place those bets on?
That's a great question. And so, even myself, when I was leaving a large company and I had to try to pick a winner, my crystal ball's just as fuzzy as everybody else's. And so the one thing that I have to really rely on is what I know about truth and science. And so we really have to look at the data, and we have to look at the data not with a bias. We have to look at very unbiased data, and we have to challenge that data. And those that really have very robust validation profiles are the technologies that will succeed. And Melissa, it's a great question. The global OEMs, because we were really focused on automotive, the global OEMs are hedging. They're making several investments in several technologies. They start with current state technology of lithium ion. But companies like Daimler and General Motors and Volkswagen, they're investing in several new technologies. They're not sure. They have to hedge. What they can't do is wait. They have to make sure that they've got investment in all these technologies. The winner's going to emerge, and it might be multiple components of winners. It might be a winner on the anode. It might be a winner on the cathode. But together, they're going to find a solution that meets their needs: cost, performance, efficiency, and above all else, it's got to be safe.
That makes a lot of sense. Okay, and we have another question from the Q&A. Someone says here, recently, John Goodenough said that he had developed a lithium battery technology with substantially higher capacity and faster energy cycling rates. He also believes that sodium can be used in lieu of lithium. Do you have any thoughts on this?
It can be, and there are deployments at the what I'll call the prototype and demonstration level. You've got to start looking about the ability and the efficiency of promoting transfer of electronic ions, and so there are many different things. Lithium is phenomenal for doing so, but there are other materials that can do it as well, if not better. They've just not been developed with enough detail and with enough cyclability to prove safe and to prove efficient for a long period of time. And that's really where the proof in science comes in. And Goodenough is talking about a couple of different things. Goodenough is talking about taking lithium ion technology today, coupling it with an ultra-safe anode, and going to a solid state format. And there's 3 significant innovations there, all of which are difficult to bring together in a single cell format. I'm not saying it's impossible. It's absolutely possible. I'm just saying it's going to take a lot of hard work to envision that at a commercial scale anytime soon.
Okay. We also have a question here. How many years do we have before we have technology for a week-long cell phone battery?
Great question. Very relevant. It gets right down to the personal use, discussion. And so I would tell you that the technology that I am working on at Zeta Energy is an energy that takes we'll call it duty cycle, or the cycle use of the current battery in an iPhone today. It's about a day if you're lucky, right? And so what we've done today with specific energy and specific capacity suggests that when we have I'll call it an equal size production rate pouch cell out there, we're going to be 3 to 5 days. And so 3 to 5 days at a step in technology with improvement, I would say that less than 10 years, we'll have a battery technology out there that runs for weeks.
Wow, cool. Okay, I'm going to ask you one last question. In this process of developing basically a breakthrough battery technology to solve problems, you also have all these hurdles, right? Like demonstrating and building scale, and can it be manufactured efficiently? Because there's all these other places where it can go wrong. To your mind, what are the hardest parts of that journey, and have you learned anything about getting through that?
Well, yeah, and I think it's the most difficult. It's the most difficult issue for most startup companies. It's going from lab scale to demonstration quantities at an industrial scale. And so maybe one of the greatest lessons we learned is to try to not reinvent the equipment. It's to look to like industries where we know they've had very high success at very high capacity. And so we looked to the solar industry for our anode, and we look to the high volume mixing industry for our cathode. And so instead of reinventing equipment, we're really going to utilize the knowledge base of industrial giants to help us deliver those solutions in like industries. These are very similar processes. We may have to change time, temperature, pressure, but why reinvent the machine? It's there. And so we can take years, if not 10 years, out of the time frame to really bring it a very high commercial level.
Standing on the shoulders of giants, right?
It's the best way.
Okay. Well, Tom, thank you so much for a fantastic talk.